Hello everyone, I'm Dinghao Liu from Zhejiang University, and I'm happy to introduce our paper, Improving Indirect-Call Analysis in LLVM with Type and Data Flow Co-Analysis. We know there are many important security applications like CFI and bug detection require precise control flow graph to support inter-procedure analysis. And to build a precise control flow graph, we must confront and overcome the challenge of analyzing indirect code targets. This is a non-trivial task because indirect codes can often be opaque and their targets are usually uncertain due to the dynamic nature. Now we have several methods for indirect code analysis. The dynamic analysis records the indirect code targets at runtime and updates the control flow graph accordingly. It is precise but unsound. And some static techniques rely on whole program pointer analysis to identify indirect code targets. It is also precise, but often unscalable, especially when we analyze large programs like OS kernels. As a result, the most widely used solution relies on type analysis, which matches types of functions and indirect code pointers. It is also called one-layer type analysis. It is common in CFI because it is sound and scalable. However, this method will introduce many false positives. To address this limitation, two-layer or multi-layer type analysis is proposed based on an observation. Many indirect codes are used as a struct field. The struct type information could be used to improve the precision of indirect code analysis. Let's see the example. For one-layer type analysis, all address taken functions with the same function type, including the return value type and argument type, are regarded as valid targets. So for the indirect code at line 16, its target set includes 4 functions. A multi-layer type analysis finds that the indirect code comes from the field 1 of struct S. So which functions are used to initialize this field? They are func1 and func3. We can see that Delta is more precise than one-layer type analysis with additional struct type information. However, only type analysis is still not precise enough because we know only func1 in this example could be called. If we combine the type and data flow information, we could finally achieve the ground truth. The data flow analysis is not to be very precise. For example, it could be field insensitive. And based on the insight, we propose the type and data flow co-analysis. The idea is simple, but when we implement this system, we need to address 2 challenges. First, when we implement the system in LLVM, we found the type representation in LLVM IRs are not always consistent with the source code. Some important information is missed. We call them broken types in our study. Note that these types are not really broken. Maybe the compiler just discards some unnecessary information in code generation from its perspective, but it influences the type-based analysis on LLVM IR. Another challenge is how to make the data flow analysis efficient and effective. To address the first challenge, we propose the type recovery, and to address the second challenge, we propose the 2-dimensional data flow analysis. Our co-analysis system contains 2 phases. In the environment preparation phase, we find the broken types and recover necessary information for our type analysis. Then we perform a multi-layer type analysis to build an initial control flow graph. In the analysis phase, we iteratively perform data flow analysis and type analysis to improve the precision of the control flow graph. When the analysis reaches convergence, we dump the CFG to support applications like CFI and bug detection. So what is broken type? We found 4 patterns that types in LLVM IRs are inconsistent with the source code, including omitting function pointer types. We can see in the example, the function pointer field of struct A is replaced by a void pointer type. Another thing is that the field of a structure may be partially unfolded. We also found that the name of structure types and the type information in optimized LLVM GEP instruction could be missed. In our system, we need to recover these broken types. We decide to use a type name to compare different types like structures. We first recover the missed type name with the help of source code information, which is recorded in the LLVM MD node. Then we iteratively recover the potentially broken structure field and the field index of optimized GEP instruction. Here we give an example of how we recover the type names according to the LLVM MD node. Before we step into data flow analysis, we first introduce the alias analysis we use, which is modified based on the data structure named alias graph. Each node in the graph represents an alias set, and each edge in the graph represents a pointer dereference operation. The alias analysis is an procedure, but flow and field insensitive. The alias analysis is performed according to the data flow analysis. Let's see the example. We start the analysis from the Indirect-Call set at line 7. The alias analysis tells us that the Indirect-Call named con is alias with a global function pointer named pscon. Then we track the data flows of pscon and find that it comes from a function argument named acon. By now, the alias set of the Indirect-Call contains 3 pointers. They are alias with each other. And finally, we track who called the function defined at line 10. And we know that 2 functions named doPF write star and doPF read star are passed as arguments. So we can conclude that the Indirect-Call targets are these 2 functions. The data flow analysis has 2 targets. One to resolve simple Indirect-Call, like the previous example. And note that we use both forward and backward analysis to improve the precision. If the data flow analysis cannot guarantee the soundness, for example, the Indirect-Call is aliased with a semicode, TFA will fall back the code analysis to single type analysis. Another target is to collect more layered type information to improve the performance of multi-layer type analysis. And we call it echo-oriented type mining in our paper. For example, in the perspective of Melta, the Indirect-Call at line 4 does not have any layered types. Therefore, Melta will fall back to imprecise one-layer type analysis. However, with the help of data flow analysis, TFA could identify that this Indirect-Call has an outer layer struct type named substring OPS copy kernel, which makes this Indirect-Call benefit from multi-layer type analysis. And in another case, for the Indirect-Call at line 16, Melta needs to analyze which functions are used to initialize the detect field of AP. And it finds that it comes from the function arguments. Melta will not conduct further data flow analysis, and it will just mark the detect field of AP as undetermined or escape and fall back to one-layer type analysis. This problem could be addressed by TFA by checking the data flows of caller functions. We evaluate TFA against 5 famous large programs, including the Linux kernel. And on average, TFA could eliminate 24 to 59% Indirect-Call targets compared with the state-of-the-art multi-layer type analysis. One important concern is that whether data flow analysis misses valid target, so we build a benchmark for false negative analysis through runtime tracing. The results show that the data flow analysis of TFA does not introduce more false negatives than type analysis. Note that for OpenSL, the main cause of false negative is a type casting between void pointers and other pointers. If we allow such casting in type analysis, then we will have no false negative. If we do not perform type recovery, the false negative number rises to more than 800. We can see that the broken types will influence the soundness of type analysis in LLVM, and the type recovery could effectively resolve this problem. We apply the fine-grained Indirect-Call analysis to CFI protection, which is practical. And we also apply it to kernel bug detection, which focuses on whether the indirect release callbacks are correctly used in the Linux kernel. And with the help of TFA, we found a new kernel bug with a much refined analysis scope. To conclude the paper, we found type and data flow call analysis is a promising method for indirect call analysis. We implement the system as TFA, and the evaluation showed that it could provide us more precise indirect call targets with soundness guaranteed. Thank you very much.